Dochit. He's an assistant professor of electrical engineering at IIT Kharagpur and a founder of Skin Curate Research in Kharagpur. It's an Indian-based smart medical imaging device startup. And he has received the BTech in Electronic and Communication Engineering in 2008 from West Bengal University of Technology, Kolkata, and PhD degree from Indian Institute of Technology, Kharagpur in 2010. And his interests are in computational medical imaging, machine learning, signal processing, and social implication of technology. And he was also here yesterday for the panel discussion and is here in person to give the talk. So I really appreciate your effort that you put in for making this a grand success. Thank you so much for joining here. Yeah.
Okay, yeah. Always a good thing to be back in IIIT. I do remember this auditorium. I had been on a few talks over here. And it's always like coming back and visiting. And now that COVID is gone, we really like to be again in this physical meetings, which makes it pretty nice. Now, I was given this pretty much a challenging topic over there. So when I got down the program, it says like deep tech in healthcare. And then just ahead of me, it was Phanindra Yalavarthi who was doing it. Now, typically, this is a very, very dangerous combination which you are choosing upon speakers. So, but then, yeah, I mean, I somehow know typically in these kind of settings what Professor Yalavarthi presents, and then these were again because we have been doing these kind of talks a lot frequently. So it was good again seeing that he had actually set in the whole stage. So for me, the job is rather easier, and I would focus rather on a deep tech. Now, there were all of these questions which were going around over there. A lot of people had this question around like your models, why to make it light, compute, speed, latencies, etc., over there. The bigger challenges are like, how do you really build that model? That's another question over there. So what I did choose is that I'm going to actually go very deep over here. I'll unfurl complete maths. That's what we'll start maybe 6-7 slides later on. And about one of these new things which just got published. This is hot out of the oven. It's about 2 weeks that it's out in publication. And this is about our efforts on how we built a deep neural compression engine. And when I say a deep neural compression engine, it's not going to compress neural networks, but this is something which compresses images. And it uses a neural network in order to create the whole compression engine itself. So what we are looking at is how you are going to build up image compressors of the future. So like JPEGs of the future or J2Ks of the future, and where they are going to bring in that next level of a disruption. So it's more of a storytelling way of doing that in the initial part, but then later on I will really get into a lot of deep maths with it. So at the start of it, whatever I'm going to present is essentially a lot of cumulative work over the years funded by several funding agencies who have been really supportive of the kind of work which we do, and I really acknowledge all of their supports. Now, this is an outcome from a major initiative which we were doing along with Intel, and it's called as the Project Myriad. So Project Myriad is about, it started in 2017. It was as a result of an award grant which we were given in 2016 for one of the challenges, where we put down a very ambitious proposal that we are going to build up a very large scale open source repository of and a knowledge base of how you can develop deep neural network based models for image analysis in the radiology space. And it not just gives you an understanding of how these technologies are getting developed. In fact, like one more thing which comes out which was beyond what we had promised is we are actually writing a book. So it's a 24 chapter book which we are putting down together, close to about 400 pages, which tells almost on a daily basis what we were encountering over the last 5 years that we have been doing this in solving it out. So it's more of to present to you, there is a separate textbook on medical image analysis, there is a separate textbook on deep learning, and then how do you really merge all of them? There is a separate textbook on image processing. So this is where we really took down all our actual blood and sweat over there, what we were encountering, every single failure instances, what we learned from a failure instance, what you can possibly learn over there, and putting down together as a book. So today's is more of like journey about one single chapter from that book. And this is about the first objective which we were trying to fulfill, which was on compressing medical images at real high density factors. So as of today, if you look into say any kind of radiology images and take a JPEG or a J2K based compression engine, you would be able to compress these images to a 10 times or maximum 20 times factor without losing out anything of a diagnostic quality. And we took up the challenge that can we really bring in a disruption. So what we are saying is, can I compress more than 400 times without affecting the diagnostic quality? And this is a story about what we really did to do that. Now, Myriad had a real multifaceted way in which we were looking into it. So one major part was definitely to look into image compressions, because you're working on image analysis. Sooner than ever, you are actually going to hit the roof line of how much of medical images you will be able to put into your storage and archives. And in fact, during COVID, with all bigger disruptions on digitization, digitalizations, and etc., whatever terms you can call as IT of the future, we did realize that the only thing we ran out was silicon and storage media. So in fact, ferrite core memory storage or any of your SSD storages were not even so popular until and unless it came down to COVID, because now you did not have enough of selenium left in the world to do magnetic storage. So everybody had to move to ferrite core memory in order to do that. You had one of the biggest stress we had was that we were facing lack of rare earth minerals because of the whole logistics and supply chains over there, and you were left devoid of silicon chips. So this was a major problem with silicon manufacturers, and that led to a very big boost in the whole field of quantum computing and quantum technologies. The world, more than pretty sooner, we realized that we need to move away from using electrons for any of our compute to using photons for any of our compute, because they are much more cheaper, much more fast, and that's where we will be going down. We will not be getting scaled down by the availability of materials in any ways. Photons can really use much lesser real estate than in order to do the same amount of compute. So while we were doing all of this, we were still focusing on how do you really compress, because scanners have become better and better. GEs of the world are pushing down chiclet sizes on the CT scanners like anything. Today, you get CT images which are 4K in size. So you typically cannot even see them on a laptop screen. I mean, you will just be seeing 1/4 of them if you are mapping to a 1 pixel resolution form. So, and you need 4K sized real viewers in order to see them. Next was, we took up this major thing and said, like, let's build screening engines. So you can either take one cancer, one problem, go deep into it, or what we said is, let's build AI for the masses. Build a playground where you solve the first level. So what Professor Funny was saying as level 1 autonomy, it was not there. If you really want level 1 autonomy, so today if you compare that with the same instance which he gave out for autonomous cars, you can get ABS, EBD as a standard fitment across the cars. And this became so because manufacturers are no more keeping this as a trade secret. This is all what is outsourced to vendors. And there are so many vendors across the world. In fact, like within India, there are about 150 plus vendors who just make ABS and EBD. This is the same thing which was done even with your airbags. Airbags still they were kept very proprietary, it was not working out. When you made it very straightforward, it went out. It was the same thing which was made with seat belts. So here also, this is what it's needed. And possibly universities are the places which can actually do that. You can create that first level of model, really subject it to exhaustive testing, get through all software quality checks done, and make the whole experiment repeatable for anybody to clone out over there. And then you have your GitHub where you put down everything over there. The only thing is that be very judicious and be very responsible when you put it on GitHub. So this is something which we ensured over here. Another thing which comes into all of this is that you will still be lacking data sets. You will have biases in data sets. And how do you really counter that bias? And for that purpose, we started working on image simulators. So initially, it was more of a pet project that we were trying to see if we can simulate images from just a basic understanding of digital phantoms. But then eventually, it went out to the point that we could generate a lot of cross-modal and multimodal data. Same patient, you have a CT image. Let's see how it looks on an MR. Let's see how that tumor looks on a ultrasound. Let's try to see if we change the scanning plane of the ultrasound, then how it will look. So these are what we were able to do. And then what this builds is, today, if you want to, say, create one model with the same patient where the tumor is scanned on CT, on X-ray, on MR, on ultrasound, it's practically not possible. The patient is going to run away. This is as simple as that. Nobody wants to spend 4.5 days in a hospital just going from one scanner to another scanner. Why would somebody volunteer? And then on top of it, it's a patient. I mean, they're already in pain. Why would they do it? You will have to now come out of the box, digitally resynthesize every single thing over there. And that's what image simulators are going to do as of today. While we built all of that, the largest contribution which we do is on the tools and techniques which we have. One is that we have explainabilities built into each of them, because that was our basis for establishing trust of a clinician on the models. I'm not going to speak much on the trust and the tests which we had done around that, but definitely we have each of these models which out on the GitHub is no. I don't know. Let's see. Hope it works. And the cable is too heavy, it's plugging out. So AI explainability was something which we really needed to have, and we have explainabilities right to the pixel. So I will not be speaking much about that, but still try to touch upon a bit of that. The one thing which Funny was saying was on how do you really do these decompositions of neural network functions over there, and you can reduce down the compute and how they work it out. So we do make use of them a lot in order to really see that these get deployed on the edge. Next is we have worked extensively on neural architecture search, and what that essentially means is that can you design your own neural architecture given a certain set of constraints. So you can put down the constraint saying that I will not be using more than say 5 picowatts to process an image. I will be putting down that I have a latency of 10 milliseconds in order to process an image. I want a throughput of 50 images per second going through this particular edge device during inferencing. Once you put down these constraints, the question is that can you really design a neural network which will satisfy all of these constraints when put into deployment? So today's story is more about how we ended up building a neural network which can satisfy all of these constraints over there. And finally, looking into it, definitely during training and everything, we had a lot of optimization and hyperparameter tuning put down into place. And one of the major things which we did is we created a very user-friendly gamified version for validating and establishing a clinical trust in whatever we build. So the whole thing around compression engines is something which is already verified by 15 radiologists. That's a separate paper which we are writing down now on how you can build up a web-based tool and then get radiologists to come onto it and validate that this compression engine is really good for clinical use. So in a snapshot, the whole activity was divided into these 5 work packages, and definitely a common denominator was about how do you disseminate and put down repositories. We published maybe about 25 papers out of this over the last few years. We are putting down some major journals as of now, and also one major book coming down as a single volume with each chapter having two GitHub repositories to support each of them, and a lot of interactive presentation materials in order to go down really deep to write to a single multiplication within a convolution and write to a single voxel of a CT. What happens right from there till the end point of looking at a diagnosis, unfolding this whole chain. There's a team which was working on it. At this wonderful people on the last column whom you see, Orunabo, Rakshit and Aditya. I mean, students who actually make that work. I mean, PIs, we always put down a lot of philosophical statements, but then the guys who make it work are the actual heroes. So they are my heroes over there who did this one. So now, standing on top of it, let me try to give you a view of what this neural compression engine was. So the idea was pretty straightforward. Now, you have multiple modalities of images, say X-rays, CTs, MR, etc., everybody. Now, your appearance of a certain organ and what you are scanning is going to be very specific to that modality over there. So how your brain is going to look into an X-ray is very different from how it looks on a axial scan on a CT, and how it looks on, say, a sagittal plane on your MR, and how it looks in a transcranial ultrasound. Every image looks pretty different. Now, it's the same organ, but it looks very different in its appearance over there. So if I really want to build a compressor, what will it have? Any kind of a compressor basically has three important parts. One, you need an encoder or a compression block. What it does is input goes an image, which is really heavy, bulky in size. Output will come down a small bit stream over there, which is much lighter. And essentially, if you compare the file size of this compressed version to the file size of the original image, this is what is called as the compression factor. So if I say that I have a compression factor of 10x, what it would mean is that input is a 100 MB image, output is a bit stream which is just 10 MB in size. That's a 10x compression factor. If I'm looking at 100x compression factor, input is an image of 100 MB, output is a file size of 1 MB. If I'm looking at 1000 times of compression factor, input is 100 MB, output is just 100 KB. This is what goes out in the basic underlining factor. Now, the next part which you need to understand is all of this bit stream which comes down, this needs to have a certain file structure. So that file structure is very important. And not in all cases that you will just have this bit stream. In some cases, you also have something called as a dictionary or a lookup table in order to get back the image from this particular bit stream over there. So that's also critical. And then you have a decoder. Now, for most medical images, why this was chosen in this way, that you have a custom encoder for all of your different modalities, and you have a and you have a very generic decoder which will just work across all of them. The reason was pretty straightforward. The compression will happen at the machine itself. So an X-ray machine is going to compress only X-ray images, and the compression is needed right over there. It's not needed at your desktop or anywhere over there. For a radiologist which they are seeing, they don't know what kind of images they are going to get. Sometimes they get an X-ray, sometimes they get a CT, sometimes they get an MR. So over there, you need to have a decoder or a decompressor which can work across all modalities over there. So this is the very standard way why we had chosen this kind of a, say a segregation of the model, or dividing it into the whole space. Now, let's start this deep dive. I'll get into a bit of signals and images and try to explain you what compression as a basis has. So, I mean, how many of you are from a background in electrical sciences? And anybody in this room who comes from electrical, electronics, instrumentation, measurements, controls? Okay, very few people. Okay. I mean, is the crowd predominantly computer sciences? Okay. Anybody from physics? Okay. Mechanical, aerospace, mining, anything? I mean, some people did not raise their hand. I mean, what's your background? Energy. Huh? I did not hear you. Be a bit louder. AI. Okay. Okay. So you guys are still, I mean, that's like a bigger mixture barrel as of today. Okay. So let me give you a very simple perspective on this one. So there is a very famous theorem which is called as the Fourier series. So this French mathematician Fourier, he came up with this interesting point and said that if there is any kind of a repetitive function, a periodic function or a cyclic function, so you might have studied about simple harmonic motion in your +2. So that's basically a repetitive function. So if you have a simple harmonic motion and then try to plot what is the trajectory of the pendulum on a flat surface, you would see that over a period of time, you would essentially get a sine wave. This is what comes. Or even on the other side of it, there was this famous experiment which we used to do, which was like you have the wheel of a bicycle and then you try to put down a laser pointer on the bicycle and then you pull a small paper out over there. You would see that the marker, the trajectory created is essentially a sine wave. So Fourier had this whole idea, and then he said that any kind of a function on the planet which is periodic in some sense can be defined by a weighted summation of multiple sinusoids. Straightforward. This is what he said. Now, that's what is happening over there on the top. Do I get my mouse pointer? I can see. No. So over here, this is what you see. So what it does is that it initially starts with a single sine wave and then tries to approximate. And then the more and more you get down higher frequencies of sine waves over there, you would see that your actual this summed up waveform starts looking very closer to this square wave over there. This is the very simple basis which we have. Now, when we do this, then that square wave over there is what is that signal which is called as x. Okay. Each of those sine waves which you have over there is what is called as D, or the dictionary of representation basis. So every sine wave with a different frequency is one basis function for me in very simple terms. And then you are going to sum them up. So there will be some weights which you will be giving. Each of those weights for each of those sine waves is what is called as the compressed bit code over there, or B. Now, if I have this kind of a maths, and this works, I mean, you're pretty much seeing this working in front of your eyes. This is going to work out over there. So if this is working, then what you would see is that over here on the bottom over here, so as you keep on increasing one by one sine waves, what you are seeing is what is the weight being given to each of those frequencies of sine waves over there, and this is the frequency of the sine wave which is being mentioned. Okay, so this plot is essentially my compressed bit code B, the frequency, and from there I can generate a sine wave which is my D. And then what you are seeing over here in this jittery kind of a pattern which keeps on growing is the reconstructed signal X, end of it. So if I want to create a compression engine, then I need to have this simple form established over there. I will have to create something which is called as a compressor, whose function is to just have inverse of D. So if I can do that, then what I am doing is my input is a signal X. I multiply that with D inverse, which will give me B, or the compressed bit code. Now this is what I need to store. On the other side, I will have a decompressor. What it's going to do is, it will take that compressed bit code B, multiply it with D, and get me a prediction of the signal, which is X hat. Now, under general conditions, X will not be equal to X hat. There will be some error which is left over there. And this kind of a thing where you will still have some error left over there is what is called as a lossy compression. There are other mechanisms. I mean, there is this very famous Huffman coding, which is an arithmetic coding for compression, which will not have any error over there, left over there. And that's what is called as a lossless compression mechanism over there. Now, so here we are just going to see of how we can create these D and D inverse so that we can achieve a very high density compression with these medical images. This is the bottom line which we want to do. Now, in the traditional world, where you have a lot of these kind of compression engines going on, the very famous and most dominant ones are the JPEGs and the J2Ks of the world. So JPEG is, I mean, anyways, any of your smartphone cameras, etc., everywhere you will be, they just have flooded it out. What they use is, they use a particular kind of a mathematical transform called as a discrete cosine transform in order to create those D and D inverses. So they are just discrete cosine transforms. So D inverse is a DCT, and D over there is an inverse DCT, is what it does. In the later on part, around the year 2000, we also got down JPEG 2K, and JPEG 2K uses a discrete wavelet transform in order to achieve that. Now, if you look back into what are the effects of compression, what you would see is that, so what we did over here is we took an image, you compressed it out, you again ran it through a decompressor, and then you are trying to look into what is the net effect being looked over there. Now, from a very far off place, I mean, you guys are looking at it from very far off, you will not be able to make most of the changes. It looks almost the same, okay. And this is essentially the question which we go to a radiologist back and ask that, if you are seeing this on your regular viewing monitor and you are reporting a certain pathological diagnosis for this one, are you experiencing any difference? This is the straightforward question. If you did a diagnosis with the raw X-ray image over there, and then you also saw this decompressed image from our method, is there a difference in the diagnosis which you are delivering to the patient? If there is no difference in the diagnosis which you are delivering to the patient, then we are equivocal. So there can be losses in the signal, but the loss does not affect the essential information which has to be conveyed. So if this is happening, then you are pretty much good. So that's what you would see, that most of your cameras will be compressing images, and they introduce certain amount of artifact. But when you look at from your smartphone screens, you really don't see anything. I mean, you don't see a disruption over there. It looks more or less visually pleasing, and all the information is present over there. So you're happy with that kind of a quality. So getting into how we built up this, the first attempt which we did was 2017, and we had this at CVPR 2018 getting published at Click. The model was a very bespoke design. We went through a lot of midnight oil burning sessions and then came up with this kind of a design which could do a decent job of about 400 to 700 times of a compression. And then for the next few years we were still working on this one. The bigger challenge was that this engine is a very monolithic engine. You have one compressor, you have one decompressor. It trains only on one kind of a data. If I change from a mammogram and go to a MR data, then it's not working. If I try to train it with a mix of mammogram and MR data together, then also it's not working. And this is where it made us sleepless. And on top of it, we had COVID. So, I mean, that was another bigger challenge which we are facing now with labs locked down. And what do you do when you have to run everything on compute? So, but then this model was not really that bad, because if you look into this particular instance over here, and if I ask you this question, that can you really identify which out of these two is actually the decompressed image? Can you really identify and tell me? The one on the right. You're trying to guess from the last presentation. Anybody, I mean, how many people support that the one on the left is the compressed image? You can raise your hand. Nobody raises. How many people support that the one on the right is the compressed image? Can raise your hand. Hi, you biased everybody's opinion. No, both are not the same, definitely. Both are not the same. I will have to zoom into and then actually see. There is one, I know there is an artifact, and only I know where that artifact is located. That's the problem. So I'll tell you later on about this one. So from there that we started this whole issue that we wanted to build this custom encoders where you could take any kind of a imaging modality over there, compress it out, and you have just one single kind of a decoder in order to decode at the workstation side of it. How do you really build? And this is the story about this particular work which we did, about how we ended up designing very high density compression engines using neural networks. And this has a lot of adventurous part over there. But I will start from a very hawk's eye view onto the whole system. So the idea was that you break down this problem into multiple subsets. One is one level of compression, say up to a factor of 50x or 100x, is something which you can achieve with a neural network. But beyond that, you cannot use a neural network any further to go compressing. It will lead to significant loss of quality over there. Beyond that point, so you start using a lossless coder or an arithmetic encoding in order to get it. An example is Huffman coding, but then over here we were using Lempel-Ziv LZ coder in order to go down to real very high factors over there. Okay. Now, if I break it down into these two problems, now your lossless coder, which is that ENC LLC and DEC LLC, those two lossless coders over there, this is something which is an industry standard available as of today. I mean, you have your WinZips of the world. They have great compression engines for lossless codings available over there. So we don't need to really invent. What we needed to invent was on the first block, on the blue, which is the coder, and then the last block in the brown, which is the decoder. These were the two blocks on which the whole engineering had to be done. So let's start with it. So this whole thing can now be looked into at a next high level view. So you just have your compressor or the C block, and now let me look into what this C block looks like. So this C block is made out of a set of convolutional block sets. So we divided this whole problem into a set of blocks. So it's still going down into the block diagram level. Now in these blocks, what we have, we divided into three significant parts. One is what is called as the NetC ICU. ICU stands for a term called as input conditioning unit. Okay. Now we took a lot of this from actual understanding of analog front end within any imaging machines. Okay, so wherever in analog electronics, the whole field of analog electronics and analog signal processing does a lot of these things. What they would do is your input would be in a certain impedance with a certain voltage level and everything. You'll have to always convert it and bring it down to a level where you can process out. So here also we had the same problem. Our images would be in a certain format, somewhere single channel, somewhere multiple channels, 3 channels, 4 channels. You go to MRs, you can get down 8 channels, 16 channels, any of those things. I'll have to bring it down to a conformal number of channels on which I can keep on processing. Okay. Now my main processing block over here is that NetC D, which is what we call as the digest block. So a digest block in a sense that this is going to digest all the information and get me only those essential basis functions which I require. Basis functions are learnt inside, which just give me the code vector. Then comes down the next part, which is called as the NetC OCU, or the output conditioning unit. So it gives my output into again a common standard form. Independent of the size of my images or anything, that thing will always satisfy one conformal constant which I really need. So my bit streams are going to be conformed to a certain standard. This is what I need. And why do I need to do that? Because that bit stream which is getting generated from the OCU has to get into my lossless coder. So my lossless coder will have certain constants of what kind of values it can handle over there. I cannot really keep on changing that, because if I do that, then the range in which I can build up those dictionaries or DLLC is going to vary really widely. So that's going to become a time intensive process for me. So now let's take an even deeper dive into what happens within this input conditioning unit. Okay. Now it really looks complicated when we sent out for the first time for review. The first thing for the reviewer was like, you have a lot of information being put down into one single diagram, because in general, most of the people would visualize neural networks as either a graph of set of operations or a graph in which data is flowing. And what we are doing over here is, you have a graph which is primarily a set of operations, and then I also have visualizations to each of the data pointers over there. So those cubes and hypercubes which you see over there, I would rather call them as hypercubes as of, I mean, you can call them as cubes because they're 3-dimensional pretty much for my case. Now, each of those cuboids which you see over there, again ran out of display. So each of those cubes which you see over there is essentially a certain tensor which represents the data which goes into it. Okay. Now how we start with it is pretty straightforward. I have a radiology image which is always a single channel. It's never a multiple channel. It is always grayscale over there. So let me assume that it has m number of rows and n number of columns which goes over there. So that input image over there is what is I for me. So you see that blue input image I. So, and it's real valued. That's why we write it down as R power of 1 cross m cross n, a very standard mathematical notation of how to denote it. That goes into the first input conditioning block. And this input conditioning block essentially has two convolution layers in 2D and with a ReLU function in between. I have the operational conditions for each of these convolutions written. So when I write down 64C, it means that there are 64 channels in the convolution kernel. Each has a spatial width of 3 cross 3. That's what I denote by 3W. It operates with a stride of 1 cross 1. That's why I have 1S. And everything is padded, 0 padding of 1 pixels on all the sides. That's why I have 1P over there given. So this is a very straightforward representation. Now once you see that you have this input going down over there, what I end up getting is an output tensor of 64 channels of m cross n. Now it's a R power 64 cross m cross n tensor which comes to me. That I pass it through a ReLU. And ReLU's thing is pretty straightforward. Most of us know about it. What you are going to do is, any value which is greater than 0 will be preserved. Any value which is lesser than 0 will just become 0 over there. So essentially it maps a full scale real valued number to a set of positive real valued numbers. So that makes it R plus to the power of 64 cross M cross N. Now you have another convolution layer where I bring in a stride of 2. So see over there you can see it as 64C3W2S1P, which means that the spatial span is now going to reduce. So if you put it down into your equations which determine how your sizes are, you would end up getting that my output tensor over here is a M by 2 cross N by 2 tensor. So I have a 1/4 total reduction in the volume, and along each of these width and height spaces, I've reduced it by a factor of 2. I again pass it through a ReLU and then get my output, which is a positive real number set only. So this is what my input conditioning unit does. And so the first and foremost thing it has to do is that it has to bring it to 64 channels, and it has to reduce the size to 1/4 of the original. This is the first thing. And independent of whatever images you are giving, your ICU is always going to do this thing. Next is my digest block, and this is where all the fun happens. What we do is, you have a lot of those dark green blocks in the middle, which you see over here. Now, each of those dark green blocks are functionally equivalent to each other. So whatever operations are inside each block is the same. And I'm just opening up one of these blocks over there. Now, what it helps me do is that whatever I give as an input, it will always scale down that input in the spatial domain by a factor of 2 on the width and height. So it essentially means that if I have small d number of units, then on the output, I will have a 2 power of d cross 2 power of d times of a scale down in my width and height. This is what I get. So now, if you look over here from my input conditioning unit, I now have a tensor which is R plus power of 64 cross M by 2 cross N by 2. And if I have small d number of such digest units over there in the green, then the output from there is going to be R plus to the power of 64 cross M by 2 to the power of, so it should be 2 to the power of d plus 1 cross N by 2 to the power of d plus 1. This is what you would be getting down over there. And here comes the first major invention which we did. So if you really want to change your compression factors, what you just have to do is you insert one more digest block over there. It's as simple as that. And when we use this term called as a digest, it was very carefully chosen. So you keep on increasing the digest, your digest pipeline increases. You keep on digesting your data more and more. It will keep on becoming smaller and smaller and shrinking down in size over there. So that's the first part on that neural architecture search. And then finally, you need this kind of an output conditioning unit whose job is essentially to convert the number of channels over here into even lesser number of channels, essentially 16 channels, to give it a conformal form. But then it does not really downsize anything on the spatial span because it operates with a stride of 1. And that's why you would see that the output is now R plus to the power of 64 cross M by 2 to the power of d plus 1 cross N by 2 to the power of d plus 1. The only control over depth, what I have, only control over compression factor which I have over here is through that depth inside over there. Now for the decompressor, you have a similar mechanism. Nothing great. I mean, if you reciprocate each of those, then you would be getting down. So you have an input conditioning unit for the decompressor, which is more of like trying to counter the effect of the output conditioning unit of the compressor itself. So it converts from 16 channels to 64 channels. You have a bunch of these digest units again over there, which are now trying to upscale it out. So essentially, every operation over here has something which we call as a learnable deconvolution, which is very straightforward. I mean, you essentially compress the channels by a factor of 4 and increase the spatial span on both the dimensions by a factor of 2. That's what you do. So your number of pixels are still the same. It's just that they are getting reshuffled over there. So this is going to progressively keep on increasing. So instead of trying to do an unpooling or some sort of a, say, an interpolation over there, which might still not give you a very good factor, what we try to do over here is that we try to learn how these interpolations happen over there. And that's what you do with a learnable deconvolution. And finally, you have your output conditioning unit, whose job is to get you a single channel image, which is finally what my target is over there. And that gives you an output which is the same in a tensor size as that of the input with m number of rows and n number of columns. Now, this is my basic structure over which I'm going to play around. So first thing, I can control my compression factor of the compressor and decompressor by using only a single factor, which is called as d. or the depth or the number of digest units over there. This is the only thing. But then we also need to understand that there can be several combinations of each of these units. So how many convolution channels you will be having, what kind of a stride you are going to operate, which will really impact what is the order of compute which is going on. So what I'm saying over here is that my middle blocks over there had 64 channels. They could have 32 channels. They could have 16 channels. They would still be getting me the same compression factor because it's just dependent on the number of blocks I have. But then why don't I choose an architecture which has 16 channels, which would have significantly lower compute, compared to choosing an architecture which has 64 channels, which would definitely have significant higher amount of compute. So this is the second part of the problem which we need to solve, because the number of parameters within a model is something which helps us in defining what we call as channel capacity of networks. So each of them, so this comes down again from Shannon's very famous perspective on mathematical theory of communication, that any single channel will have an information capacity, or what is the capability of this channel to pass two such symbols so that they appear as intact two symbols at the end of the progress. That is what we wanted to do. And this thing for a neural network is always guided by the number of free parameters or the number of trainable parameters or weights which you have within a neural network. So now what you can tell me on the other side is that let's take a larger capacity model. So let's take 64 channels everywhere. And then if I don't need 64 channels, maybe I can do the work with 16 channels, but then I'm safe. I mean, I'm not going to lose out on the bit. I will not lose out. So it's like I want to transmit water from one place to another, and for that I would barely be needing an 1-inch diameter pipe. But then I come and say that, okay, let's be more safe over here. I use a 4-inch diameter pipe. And a 4-inch diameter pipe costs significantly more than a 1-inch diameter pipe. A 4-inch diameter pipe for you would be costing about 80 rupees per feet. And if you're looking at a 1-inch diameter flexible pipe over there, that would barely be costing 8 rupees per feet. Now, there's a significant difference which comes down. I mean, it's just an increase by a factor of 4 on the diameter, but then the cost at a factor of 10 increase over there. So here also it's the same problem which happens, that your compute is the cost which is going over there. And when you are running it iteratively over and over, what you need to really start looking into it is that your electricity expense is going up. Now, I don't have that carbon crediting over here, but we were really trying to do. So we found out this one. So it was something like, if you compress to that particular level with a JPEG, it's like running your any of your standard like non-hybrid cars, petrol-driven cars. For so 1 mammogram would release enough of carbon, which is equivalent to driving that fully loaded car for 100 feet with a JPEG. And if you compare with ours, it's barely about driving 1 feet. So this is the difference which comes down over there. We are not looking at it today, but definitely it's coming much sooner than ever, that we will have to really consider, be very cautious about carbon budgets. Now, coming to that point, that why I really want to scale down on these number of channels as well, because that's going to bring down my compute, and that's a very important factor. But that's not a very trivial game to play. We need to understand a certain factors over here. Now look over here. The thing which I'm going to modify is each of those convolutions over there which you see, they have a 64 C combination, which means that every convolution just has monolithically uniformly designed system where I have 64 convolution channels. Okay, it's a convenience bias, I would say. It's comfortable for me to write down one single block and then call down the same block iteratively within my PyTorch and then get that definition written. I don't have to write down definitions every time. So now what we decided to do is, let's design a certain factor which we call as scaling factor. So first we decided to go and find out what is my cost of computation. Cost of computation means that for every single pixel to process, how many operations do I require? How many mathematical operations? So what I need to do is logical operations, everything which is happening over there. I'm not going to open up the computational complexity one. That's a work which we do separately. So once you open it up, there are in fact like several tools in the market which you also get down, which give you an approximation, not necessarily always the exact value over there. Then what we did is, we said like, if there are d number of such channels and we keep on changing these channels. So how can you change? There can be two different ways. One is a depth scaling, which is, you saw those digest units which had D. So if I increase one more channel over there, then there is a factor by which I am scaling. So if my starting point is a small d equal to 3, and next I go and insert one more d, then my alpha factor over here, which is my scaling factor, is going to become 4 by 3. Look into the first equation on the right hand side. The next thing is what we call as a width scaling, which is you have those 64 channels over there and I can change it. So say my beta over there is 0.5 and my 64 with a 0.5 multiplied would give me a new network which will have only 32 channels. Now what we do is that if you do both of these things, we found out from an empirical point that you would see that your alpha, if you scale a network by an alpha, the compute scales by alpha. If you scale a network by beta, which is the width scaling over there, then the compute scales by beta square. So if I'm reducing, it will reduce by beta square. If I'm increasing, it will increase by beta square. What we did is, we said like let alpha beta square be a certain factor which we called as rho for us. And now, if I can, so now what I can do is, I can have rho equal to 1. And what that is going to give me is a set of alpha beta combinations such that all of these networks will have the same compute complexity. They can have different information capacity, but they will all have the same amount of compute complexity over there. There can be another option in which I can say that let rho be 1.5. That's exactly what we did. If rho is 1.5, then what I'm saying is that I want to get all of these alpha beta factors such that my compute complexity increases by only 50% over there. And that's going to unfold and give me a set of models. So now what I'm doing is, I give you an objective function centered around which you start with a single model, and you can now create a whole family of several models around it, which will satisfy a certain constraint. So that's what our objective was. Now once you do that, you would see that under a certain condition of, so you're keeping down this condition over here, where your rho is 1.5, and your d is made as 1. This is a new compressor, where I made down d equal to 1, starting from a d equal to 3, which means that my alpha factor, which was my depth scaling, is now 0.33 or 1 by 3. If that happens, then I need to have an increase in beta over there, otherwise my compute capacity will not increase. So if I increase that, then my channels over here, instead of being 64 channels anymore, they increase to 134 channels. So this is another architecture which satisfies the same problem. It just has 50% increase in compute complexity than the previous one. But then the depth has decreased and the width has significantly increased over here. So how do you really get this set of things is what is guided by this particular objective. Now once you do that, what you can do is, you can end up scaling your compressor, your decompressors, everything which go down in the same way. And you will get down a candidate set of models. Now you have a bunch of models over which you will have to choose. And that's what we are trying to do over here. Now the first part, the first problem which we want to do is that I want to have a custom compressor and a generic decompressor. Now what that means is that I have multiple data sets, some for X-rays of the chest, some for mammograms, some for X-rays of the bone joints or fractures, or all of these. I can have it for MRs of the brain, of the abdomen. I can have it for CT of the lung, and then each of these things going down over there. Now once I have that, what I can do is I can initiate this kind of an objective and then train a bunch of models of encoders and decoders over there. But then each of them is trained to a certain modality only. It's not something which works across all modalities. Now what I do is, when I initiate all of them and train all of these models, now there is a whole factor on channel capacity which is going to come down. Now in order to look at what is the end impact of that channel capacity, let's look into the SNR of the reconstructed image, the peak signal to noise ratio. Okay, and this is the full reference peak signal to noise ratio, so you can do it through an MSE route as well. Once you do that, you can find out one model per modality which has the lowest reconstruction error. But then every modality will have a different architecture which comes to you. Now this is the next part of it. Your custom encoder problem got solved. So every modality you got down 1-1 architecture. Next, I need to create a single decoder which works same for all of these modalities over here. So I need to train that. So what we do with that is that in order to seed that, we start with this next set of experiment, which is that I have a different depth and a different width combination for each of them where I got my optimal. But can I generate a series of models which are analogous to each other but at different depths, which means that for CT compression, can I have for d equal to 1, 2, 3, 4 at different widths, but then all of them will have the same compute capacity, which means that my rho is set down to 1, and then I have this bunch of models coming down to me. Now for each of them, I can now have a separate, I can have a unified decoder, which is an average value of combinations of all of these widths, not just the depth. Because for d equal to 1, I know for every modality what is my width coming down. I take what is the average value of the width over there and generate a decoder with that average value of the width available to me. Now once we do that and we train it out completely, then we would end up getting that for every single modality, for every single depth, you will have one combination of a coder, and you will have a decoder available for every single depth available to me. So what this empowers me to do? So has anybody ever tried compressing a bitmap into a JPEG through like using your Python scripts or MATLAB? Has anybody tried doing that? Or even on your any image standard viewer, when you it gives you this option like save as JPEG, and then it will ask you a quality factor over there. You can vary this quality factor. Now what we did over here by doing this is that d, this small d, is essentially going to control my quality factor. So now I can say I want a very high quality image, then my d has to be lesser. If I want a so-so quality image, then my d can be higher. So now for every of these multiple quality factors, I have a set of compressors and decompressors which are getting generated for me. So finally, when you have this, let me come to this final diagram, which is what helps you understand. The final stage is that you got all of these architectures, everything working down on smaller data and everything. You just need to train it. The training routine was very simple. For every modality for a given depth, for d equal to 1, you have say 11 modalities. For every modality, you have one compressor over there. For d equal to 1, I have only one single decompressor. What I do is I train each compressor with that modality specific data, and the decompressor is learning to decompress across all of them. So it's multiple networks on one side and a single network on the other side which is getting trained. And this keeps on repeating for d equal to 1, d equal to 2, d equal to 3, d equal to 4. For each of them, you finally get this one. Now once you have that, let's look into what a visual performance looks like. So this is an example where so this is a MR of this is an MR of the knee. Yeah, now I remember. Oh, it's already written. I mean, with images, the problem is that I barely tend to read what is there, and I've now become more of like a radiologist. I look into the image and try to find out what was this. So on the left-hand side is an original MR of the knee. In the middle is what we got down through our method. This is for d equal to 3. This would have an effective compression after Lempel zip coding of I think about 200x or something. These are smaller images. I mean, these are about 512 cross 512. If you have like bigger size mammograms, which are say 3000 cross 4000 pixels over there, you can get compression factors about 700 times. We are now working down with a newer data set, which is 4K sized CT scans. We are experiencing like 700 plus on those. I mean, 4K is like, it's also almost like 2000 cross 2000 pixels on the, so these are very new kind of scanners. If you compare it with JPEG, now this is the best of compression factors which you could get out of JPEG. You can see your very clear-cut patchy artifacts and everything coming down over there. Now, that's where I come to an end. Yeah, pretty much in time. I can take in a lot of questions over there, and I again throw this quiz open for all of you guys. So, and this pair of image is not the same as the last pair of image. So that pair of image was from CVPR 2018. This pair of image is from Circuit Systems and Signal Processing. This current paper, which is 2022. Now can you tell me which one is real and which one is the compressed one? Left-hand side, all leftists who say that the left one is the compressed one can raise your hand. Only one. Hey, raise your hand full. Full height hands raised. Support 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. How many people support that right hand side is the compressed one? 1, 2, 3, 4, innumerous. And the population has a bias because the left hand side is the compressed one. This one I remember. Huh? I don't know whether this lets me zoom. This does not let me zoom. Right one doesn't have the artifact. No, left is the compressed. No, I'm trying to do that. The only thing is that now it's and I will tell you the artifact is a very different kind of a thing. You see this. These 700. So you see those small disk-like structures? They are microcalcifications. So on my screen, yeah, it's much more visible. I mean, I hit 400x. Done. I mean, my PPT won't let me zoom anymore. It has an uncanny sharpness. It's not supposed to be that sharp. The reason is very simple. You are in the X-ray limit. You hit down on micron-sized objects over there. You will always get down a Compton scattering. So it has to have a diffuse behavior over there. And in the original, you would actually see that natural diffusion. And you can, I will show you on the screen. You can see that. So it's very sharp. It's unreasonably sharp. Now, typically, you would always associate that a very sharp, clear, high contrast image is the one which is not compressed and is the real one. Here, it just defies it because there was a physics principle which is defied. So you will have Compton scattering effect over there, and we were not able to see that. And that's the one which is my identifying artifact of how I say that whether this is not. And this took us time. This really took us time to figure out. There was only one radiologist who was really that clever. She zoomed into it. She pinch zoomed it into it and then said, no, this is, I'm pretty sure that this one is. And we said, like, this has the highest compression, this has higher contrast scores. Then how are you saying that? Then I'm pretty sure. Just look into it because, and then she came back to this phenomena and said, like, this is the reason why it is. Now that brings me to the other fact, which in fact, like my previous speaker, Funny, was also illustrating that, I mean, a larger thing it helps us when doing medical image analysis of this sort is that we have a background in medical physics. So we do understand how those imaging systems work and everything. So if you're doing it even for your camera systems or anything, I mean, you can have your degree in AI, but then understand the physical world. That's where a lot of answers lie. Otherwise, it can make it very different over there. So that's all from my side, and I'm open to taking in any questions, any queries which you might have. And finally, I wanted to do a advertisement for a position I'm hiring. So if anybody is interested for that one, you can, or you know somebody who might be interested for that one, but this is a postdoc. I don't think there are any postdoc eligible candidates over here, but definitely pass on the message. Yeah.
Yeah, very interesting presentation. The one question I have is in terms of the, if I compress it and send it to some third party, right, and they need to decompress, what is the overhead in terms of, I need to send them the decompression.
So yeah, so
right?
as of now, it's the same
compared
thing.
to the standard methods, for example, JPEG, I send a JPEG image, they decompress. versus I send this, what kind of overhead do you see?
So the decompressor is 7 to 10 times faster than J2K, and about 40 times faster than standard JPEG.
In terms of what additional information you need to send apart from the image?
So you have the bit stream and you have the lookup table. I mean, anything standard. I mean, our file format architecturally obeys the same principles as what you would do for JPEGs or J2K. So you just have a header which has a lookup table for your decoding. And then, so for us, that decoding is my, say, the Huffman code table or the code book which I have for my lossless coder. And then the rest is the bit stream. You have some additional header components over there which just specify what was the D equal to factor which I had been using, because you will have to pull out that decoder. So you have a D equal to 1, D equal to 2, D equal to 3, D equal to 4. These 4 decoders are available over there.
Right, okay. And also using, right, so the objective is to reconstruct such that there is no loss or there is no appreciable loss. Is it the innovation here that reconstruction such that there are no diagnostic mistakes?
Yes.
Has that actually turned the whole?
So the final deciding point, like at what depth I'm going to do and what is my tolerable compression factor, is what is done with the human in the loop study. So we had 15 radiologists who were given down these things under different compression factors. And then there was a Leica test study. A Leica test study is what it says is that I always give you the reference image and I give you the test image under say, and then it asks a set of questions. The underlying factor is that, is there any noticeable difference which will impact your clinical outcome, clinical diagnosis? And then what we do is, so if I'm giving a mammogram, then I will give the set of questions on a BIRADS mammo sheet. If I'm giving, say, a lung scan over there, then I will give down the lung rads. And then I will be asking this one. So what is your base diagnosis based on the original image? And with this compressed image, if you're doing a diagnosis, is there something which you are missing over there? And then you can say, like, you have this, like, I have a just noticeable difference. I don't have any noticeable difference. I have a major significant loss. I don't see a pathological loss, but maybe the background is lost out, something of these. These are set of questions. And then what you can do is, so Leica is a standard psychovisual test scoring system. So it has a standard mechanism on how it's done. And then you come out with a score. And more or less what we have seen is that these like the findings from a visual perception match very closely to the scores which come down over here.
Yeah, one last question. Is this representation?
So in fact, like on this one, what I would say is like when, so I did not say on that one, on the paper we had given like for what modality and what resolution, what is the depth which is recommended. We also have that particular table being given out. Whereas for a system integrator, when they take in, I mean, it says just a bunch of codes on OpenVINO. Completely optimized, given everything certified. I mean, somebody who is taking it down as a software guy is just going to pull in all the codes, but then you need to give a recommendation that for these ones, if the DICOM tag says these things, then use only these ones and others are invalid for that.
Is this representation useful for other tasks like object detection, segmentation?
So we had done it, so currently we are running it for a lot of dashcam videos for autonomous driving as well. So there, the last thing was about 2000x is the compression factors which we are able to achieve. I mean, some things which standard J2K will never be able to achieve, and then we are now comparing it against HEIC and HEVC and trying to look into it. But then these are not yet dashcam videos, these are just single image based. The next version of this one is what is getting built for videos where you also have a temporal compression on top of it to see that we can further do it.
Yeah, I was about to ask this question about videos. Can we do it for high definition video?
We can. I mean, so
that's one. And second,
my belief is we can. We are working on it. I don't yet have the model. So the final answer, I don't have it.
Yeah, second question is, I think, a follow-up from the last question about actually, can we use the same viewers of what we have, or you will supply a custom viewer kind of thing to view these images?
Okay, so what a standard medical viewer has is very straightforward. So a viewer is just to show you everything after a bitmap comes to you. And for coming from a file format to a bitmap, it uses third-party libraries in order to do it. So what we do is of a similar nature. So we just give you a decoder over there. So you get down your file, you decode it, you will get your bit stream over, you will get your bitmap, and then you do it with. So that's how we are packaging out everything and releasing it out.
Professor Devdutt, one question about the use of Huffman coding. I think this isn't this a good candidate for Huffman coding? Because after all, you are just there are large number of features which can be categorized, classified into one group.
If you let me go back to that one. So if you look over here, then this encoder, the lossless coder, it's you can use a Huffman or you can use a Lempel-Ziv or anything. Any of these arithmetic coding will work out. So that we leave it to the choice. I mean, this in fact we don't do anything with this lossless coder over there. So we have done different kind of tryouts. We initially used to do a Huffman. These days we do with a Lempel-Ziv. LZ77 is what we are doing as of today. But we leave it to different people. I mean, in fact, you can even put down say some sort of a privacy protection code and a compressor together over there as well if you want to. So we are using just the academic part of the re-implementation version. So that's the reason why we say like this is any lossless coder, we leave it to the end customer to, we are not going to give out. Because we cannot have any kind of a support licensing or anything given with that one.
Okay, so I have one practical question here. So you are trying to take multiple modalities, right? And trying to have an encoders, which for independent encoders for each of these modalities. And then you have a unifying decoder, right? And how do we see that being applied in the real setting where a radiologist who's going to scan using different scanners, and then the images are stored in cloud and then being used? So how does the entire process of image compression is going to work there?
Yeah, let me open up this particular slide. This one might help you understand. So your custom encoders, say for the X-ray is what is sitting on the X-ray machine, for the CT is sitting on the CT machine. So the compression happens right at the machine where the scan is happening. The decompression happens at the viewing station of the radiologist. In between, you have your compressed file, which is stored on either a institutional PACS or a cloud-based PACS, or you can have like any other long-term cloud storage or anything over there. You don't need to see the image or open up or decode anything. It's just a file which is sitting over there. You have file pointers on your database. You access it out. When you get it down on your local workstation, the local workstation needs to have one single decompressor. That's the bottom line. And then that's how this thing was arranged and done.
Okay. Thank you so much, Professor Devdutt, for coming here and enlightening us on this topic. Thank you so much. Yeah.